just going to gloss over this because we've already kind of completed it. Our knowledge from last week, Asel, could you close the door but not lock it, please? If we ignore air resistance, then the acceleration will be that of 9.8. After our first topic, we will consider air resistance, but that's later on in this term. Here's a velocity time graph, positive velocity. There's a point in time when your velocity is 0, changes direction, negative velocity. Now, could we please just analyze or highlight a few things? This is the displacement upwards. That there is the turning point, the point at which your velocity changes. And then down here is your displacement downwards. We can get all the usual stuff. For example, the total time was 8 seconds. But because we've got a constant gradient, we can split things up and we can use some laws of symmetry. Obviously, this is our displacement upwards, and this is our displacement downwards. Okay? And if all things being symmetric, we can say that the time up and time down are equal, 4 seconds and 4 seconds. Okay? Yes? There's one at the front. Come and grab it. There's one at the front. Come and grab it. Now, let's analyze this a few different ways. We've just learnt some equations. We could figure out S equals ut plus a half at squared. Let's just do the first half. We can chop our journey up. Okay? So if I said calculate the maximum displacement, all right? Well, the maximum displacement is when it's halfway through its journey, so we could split it into 4 seconds. Let's set t equal to 4. So we would go 39.2 by 4 plus a half of negative 9.8 by 4 squared. And that would give you the greatest value. You would get plus 78.4 meters. Okay? We could also check this bottom part. We could use the same equation. I could set it at here. If I just said, let's split this into one new scenario, let's set u equal to 0. Let's look at the falling half. Let's go S equals u, same equation. But now we would go 0 by 4 plus a half of negative 9.8 by 4 squared, and we would get negative 78.4.
So what's u again?
U is the initial velocity. So here's the next thing. Let's look at the entire journey. So I'm going to say, all right, let's go, same equation. Go for it. So if we set time for the entire 8 seconds, we should get an interesting number. We're going to go 39.2 by 8 seconds plus a half of gravity by 8 seconds squared. We'll split these values up. We're going to get, the first term is, oh, hang on, I haven't worked out the first term. You're going to get this value, 0. Okay? I didn't actually figure it out. You get something like plus 280 minus 280. Your calculator's going to spit out 0. Okay? So again, we can use that equation for any time interval from 0 through to 8. You put in your value and it'll spit out where the object is. I can say, where is the object 2.3 seconds into its journey? Well, 2.3 seconds, and it'll figure out what the area of that is. Where is it? 5.7. And it'll add that value, and it'll tell you where it is. Okay? There's another equation we can use. Let's just use another equation to confirm. Let's go another Suvat equation. Let's go v squared equals u squared plus 2as. And if we wanted to rearrange for s, Okay. Now, obviously, we would need knowledge of our velocities, and we've got them. I've told you these values in this table. You've noticed, hopefully, that I've chosen those numbers. They are actually multiples of 9.8. If we use multiples of 9.8, then we get a 0. If I started at 40, then after 4 seconds, it wouldn't be at 0, it would be at plus 8. It would still be travelling upwards. It's not yet at its turning point. So I kind of made them intentionally to be multiples of 9.8. Let's chuck in our values. Negative 39.2 squared minus 39.2 squared over 2 lots of negative 9.8. You probably don't even need a calculator here, gentlemen. What do you think the top of that fraction is going to spit out? 0, yeah. 0 meters. Okay. Or if we wanted to find the maximum, remember the key point is the maximum is when it's got a velocity of 0. If I throw anything up in the air, ready? Here we go, yay, and then it falls back down. When it was at its highest point, it was stationary. That was the point at which it went from going up to going down. And so we can make a little trick. I know that its maximum displacement is when its final velocity is 0. So if I wanted to figure out its final velocity, I could just set v to 0. And then, using that equation, we should get, what number do you think we should get? I'm going to scroll up. Yeah, we'll get that number, 78.4. Okay? So you do your negative u squared over 2a, and that should spit out its maximum displacement of positive 78. You get a double negative. See? This negative, by the way, is outside, so he doesn't actually belong to u squared. It's opposite u squared over, so you get a double negative, and your equation spits out a positive value. So our direction is still conserved. In all of these equations, your calculator is going to give you the direction of your velocity or your displacement as well. Yes?
So should we be using 9.80 or 9.8?
9.80. Yeah, I'm just being lazy and saving paper.
Okay, you gotta add that.
I'm not saving, I'm saving time. Okay. Gentlemen, can we just sketch this for me, please? Seems it's here. If we plotted a position time graph, we get obviously a quadratic. Okay. And so even our quadratic, we can split down the middle, and there's some symmetry going on here. We can still say that our time up value is equal to our time down. And so if we had 8 seconds here, and 4 seconds there, and 0 seconds, we can still say 4 seconds up, 4 seconds down. Okay. And we can still say here our gradient, if I asked you to draw a tangent line, if I wrote the following, would anyone be shocked? Does anyone know what that means? No? All right, we'll just write tangent. Because remember the gradient. Should I say gradient? Whatever.
Gradient.
Remember the gradient of our velocity time graph is the gradient of our position time graph gives us velocity. So that's the turning point of our quadratic. Have you guys done quadratics in maths?
Yeah.
Yes.
Do you know the equation for the turning point?
Yeah. Y equals x minus b.
Minus b on 2a. Correct.
Oh, yeah.
Yes. Now, I haven't drawn this yet, but we're going to, yes, I put it up on the whiteboard. I think we've got maths talk y as a function of x equals ax squared plus bx plus c. And if we chuck it into physics talk, it's displacement as a function of time is a half at squared plus ut plus s initial. Okay. Now, our turning point, we're just playing with these coefficients. Now, our a coefficient, remember from our motion capture activity, what are we expecting our a coefficient to be? Negative 4.9. And now let's consider our b coefficient. That's the initial speed. Okay? So, this is in maths. I'm going to color code this. This is maths talk. We can rewrite our turning equation into physics talk. It's actually negative u over g. Ooh. Okay. Which shouldn't surprise you too much because there's an equation that we've learnt already. T equals v take u over a. Right? You remember that from your equations of motion? At its turning point, the final velocity is 0. So if I set v equal to 0, what do we get? We get negative u over a, where acceleration is gravity. Okay? So for any object thrown up, any object in parabolic motion or in free fall, we can time it. We can use all of these little tricks. We can figure out the time it took to get to its highest point. From there, we know its velocity by rearranging this equation. All of this stuff. Let's just quickly check. If I wrote negative 39.2 over 9.8, that's the speed I threw it up, the velocity I threw it up. Negative that to negative, we get 4 seconds. Oh, sorry. I should have added the minus there. We get 4 seconds, which agrees with everything I've been telling you. So, there's a few little hints that I want you to know, just to have in your back pocket to help you when you're solving some of these questions. The hints are, at S maximum, that's at your maximum displacement, your velocity is 0. Okay? And that was the example when I threw my pen up in the air, I knew that at its highest point it was stationary. And then the next little trick, on level ground, T up equals T down, which is your total time on 2. It's half the total time. Okay? And hopefully, if you're very good with your quadratics and your velocity time graphs, you can see that it's symmetric. And so if it's symmetric, we get equal areas on either side of the x-axis. We get equal base lengths. We get equal heights. Everything's equal. We can slice both of our graphs through down the middle, and they're symmetric. So these two little hints are just from that symmetry. So, everyone, get your stopwatches out. I'm going to throw this up in the air. You're going to time how long it takes between me throwing it and me catching it. I'm going to go ready, set, go. And on go, you start your stopwatches. Okay? Ready?
Throw and catch at the same point.
I'm going to try and catch it on level ground. Ready, set, go. Stop.
0.96.
Alright, and we take the, say again.
I got 0.9.
What'd you get?
1.06.
1.0. What'd you get? What'd you get?
1.10.
What'd you get?
1.02.
What'd you get?
1.02.
What'd you get? 0.03. Alright, I just took the average of all of that. Let's go a time of 1 second. Now, we don't have any space. Oh, look, here's a question. You have to do exactly the same damn thing. Let's just go to the whiteboard. a bit of dead time on the YouTube. Here we go, gentlemen. 1 second. I know that halfway through its flight, it was at its highest point. So there's my little trick. I also know if I split it up, on time up, it took half a second for its velocity to be 0. And I'm pretty confident at the rate that our velocity is changing. That's gravity. So I can figure out the speed. If I go v equals u plus at, u equals v minus at, equals 0 minus 9.8 by 0.5 gives plus 4.9 meters per second. So it left my hand traveling 4.9 meters per second upwards. If we multiply by 3.6, we get around about 18 kilometers per hour approximately. So it left my hand at 18 kilometers per hour. Okay? Now it didn't hit the ceiling, and it left my hand from about here, so I'm expecting a maximum displacement, between 1 and 1.5 meters. So let's just quickly check that. S equals ut plus a half at squared, 4.9 by 0.5 Could somebody please solve that for me, because I'm not that good at maths. No, I'm not even going to try. It's 4.9 minus 4.9. Can we?
1.225.
Sure. It's what's that? That's a half minus a quarter. It's just going to resolve to 0.25 or 4.9, which was 1 point.
1.225.
Okay, so 1.2 meters. And when I threw it, yeah, it's about 1 meter and 20 centimeters. Yeah, sure. Sure. There we go. Done. So that's just a little trick. There are some questions over the page, such as this person standing on. You're going to do exactly the same scribbling as that, and you'll be able to solve it. Okay? Have a think, gentlemen. If you get a soccer ball and you go outside and you boot it as hard as you physically could, Tristan, what did I ask? What did I say? No, you didn't. You didn't. If you go outside with a soccer ball and you boot it vertically upwards as hard as you physically can, how long do you reckon it could be in the air for? 3 seconds.
Yeah, Joe's going to be cool.
Maybe 4 seconds. Okay? So, shush. That's an easy way for you to figure out the speed it leaves your foot. You just need to measure the time. You could film it with an iPad and it might leave the screen, but you could use motion capture.
Wouldn't you have to
Let's just do this question quickly, and then I want to talk about the quadratic, and then I'll let you guys complete the remaining questions. Here we go. Oh, let's just go. We're still using our skills, Patrick, that I asked you to remember a couple of weeks ago. Let's highlight the important stuff. Okay, and let's add 9.8. V equals question mark, U equals 0, T equals 2. And even though we're given the height of the building, we don't actually require it for this question. Okay? This is a very simple one, V equals U plus AT. And again, we don't leave it in math talk, we convert it back to physics talk. Now, for this one, I hope you got all that written down. Now we do need the displacement. We're going to displace the rock 25 meters, and it's accelerating at 9.8. We don't know what the speed is when it hits the ground. We only know the speed 2 seconds after being dropped. We know U, and we're asking for question mark here. So, without knowing V, we can't use our easy Suvat equation. What equation could we use? And you might need to go back to your booklet with all of the Suvat equations. No, because we don't know V. We don't know V, so we cannot use the VUAT. We've got to use the equations with S in it.
S equals.
Go on. Half, that's the one. Because we dropped it, it becomes a very simple question. Well, we'll have to rearrange it first. Times both sides by 2, divide by A, and take the square root. I hope you're all good at rearranging. If I ask you to rearrange for T, you do your reverse BIMDASI stuff, and there's your equation. So we can now go the square root of 2 lots of negative 25 over negative 9.8, square root of 50 over 9.8, square root of 5 point something, we get 2.26 seconds. So just be careful, gentlemen, even though we were given that the balcony, or where was it being dropped from? Building. Even though the building was 25 meters high, the displacement for the rock is downwards from its initial point. So that's why I had to put in negative 25 meters. If you tried to put in positive 25, your calculator would not be very happy. Yeah, it would give you the square root of a negative and go error. Because if without putting that negative, that's like I'm standing on top of a building and I I drop an object and it goes that way, and I want to know at what time is it 25 metres above me, your calculator's going to go, no, it was never up there. Doesn't work. So that's why if I drop it, I'm displacing the rock negative 25 metres because we're accelerating it downwards at negative 9.8. Okay, so there's your little things you've got to be careful with your directions and your maths. Yes?
In a question like the first, where you're given the displacement but it doesn't look like you need it, would we do something like check to make sure that the rock hasn't hit the ground yet?
Well, I when I made this question, I checked that after 2 seconds it was still in the air.
Yeah.
Yeah.
In the test, would we want to be checking?
No. You treat everything as working. Okay? And yet, sometimes that's a red herring for part A. You didn't actually need that number, and sometimes that will occur in tests and exams. You'll be given values that you don't actually need. Last question. Again, we've got extra info here. 2.26, negative 25. There might be a plethora, or there's probably 2 or 3 equations we could use. I would suggest you pick the easiest equation. Which of the Suvat equations is the easiest to solve for V? Yes. I wouldn't go V squared equals U squared plus 2A. You could do that if you... Oh, actually, that comes out quite simple. You could go S equals VT minus a half AT. You could rearrange these two, but they're trickier, okay? So I wouldn't even bother. I would just go straight to the simplest equation. And out spits 22.1 meters per second. Now, it just asks for the speed, so we only require the magnitude. If it asks for the velocity, we would have to include the direction.
So we'll do 22 because there's 9.8
And it is 9.80. So again, that's just me. Sorry, I'm being lazy. I always simplify. But in the question, you are given all your values. And in the data sheet, all of your values will be given to 3 sig fig. Unless we're testing you on your working scientifically skills. Yeah? Which might, then you have to play with sig figs. Now, I just want to, because you kids are smart, I just want to show you that you can use V squared equals U squared plus 2AS. You can solve V equals the square root of U squared plus 2AS. You can do this. No, well, no, and there's a bit more to it. What do we get here? The square root of 490.
So positive.
Yes. What's the square root of 490? That's right, everyone, it's 22.1. However, oh, wait. The issue with taking the square root of something, I don't know what I'm doing. I've lost it so early in the game. Here's the problem. We get an ambiguity. Ambiguity. The maths is saying that that value could be positive 22.1 or negative 22.1. You would have to use your logic that if you strike something, if you hit the ground by starting from above it, then the only way you can come into contact with the ground is to be traveling downwards towards it. Okay, so you can sometimes in year 11 and 12 physics, you would sometimes have to discard the alternative. And I want to show you why that is. Because this equation comes from quadratics. This equation comes from, are you ready? Are you ready for this? Are you ready? Are we ready? Are you ready? Don't draw this. Don't draw this. This is the shape of our quadratic, right? And here's us atop a 25-meter tall building, okay? However, what we have done, we have fit a quadratic equation to the motion of our object between t equaling 0 and 2.26. However, that quadratic goes on. It exists in negative land, and I'm going to draw negative land in a weird, spooky dashed grey. It exists in negative land. So what we just did is we solved that there's 2 times that this quadratic was at s equals 0, or sorry, at s equals negative 20. There were 2 times here when it had a negative 22.1, and there when in negative land it could have been thrown up and it's slowing down, and then it gets to your hand and then you drop it and it becomes real. That value, this whole term here, that tells us the tangent for a given height. Okay? And so if we say if it existed in positive, in negative affinity and positive, remember quadratics, they go on forever. They just keep going and going forever to infinity and beyond. However, we only want it to exist for 2.26 seconds between 0 and plus 25. We're only caring about the real quadrant. We don't care about negative s and negative time. Yes, Matthew?
So, shouldn't the answer we had up there have a
Yes. So at the very end of it, you would say equals 22.1 meters per second. Well, in fact, we're just asking for the speed. So we just...
I mean, the one we originally had, is that negative?
No, because we only want the magnitude.
Oh, okay.
We just want the amount.
So in
Yes.
this case, the positive and negative doesn't even really matter.
Well, if the question said determine the velocity. Now, the key thing is this equation kept our direction. Your calculator would spit out negative 22. This equation removed it. Okay? Now, let's venture into the quadratic equation. Have you guys done the solutions for the quadratic equation? Who can spout out the quadratic solution?
X equals b squared minus square root, plus minus square root of b. No.
All right, a couple of you need to write this down. Ready? Maths talk. Y of x and s of t. I'm just going to put that there because I'm just going to simplify that a half of gravity. Thank you. Now, in maths talk, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. And in physics talk, it's negative u plus or minus the square root of u squared plus 2as. Sorry, let me try that again. Yeah, we'll leave it as that, plus 2as over gravity. Now, I'm going to throw in a very simple quadratic. Here we go, boom, boom, done. Now, t, u, imagine we had all the values. And again, let me just highlight, I did this on the previous page, but I'm going to do it here, that we're always going to have that the coefficient of your x squared is always a half of gravity. It's always minus 4.9. The coefficient of our x is always the initial speed that the object is released from. And our y-intercept might be the initial displacement of the ball. Now, if it's on level ground, here's the cool thing. If it's on level ground, that term goes away. That term goes away. Okay? We get something interesting occurring. If we set s to 0, right? Hang on. We get an expression, negative u plus or minus the square root of u squared. What's the square root of u squared? U. All right. So, if we write here, let's just roll with it. It doesn't matter how far we get, but if s equals 0, then we get t equals negative u plus or minus u over g. We get, what's negative u add u? 0. Or, what's negative u take u? Negative 2u over g. Which just happens to be twice the turning point. What's half of negative 2u over g? So I told you the turning point was negative u over g. This time here would simply be 2 of that. Okay? So if I throw it on level ground, it's going to be at my hand, level ground. If I throw it on level ground, it's going to be there at t equals 0 or t equals 2u over g. If I throw it faster, then what I'm doing is I'm making my quadratic steeper, and then it's going to take longer to come back to the x-intercept. If I'm in a weaker gravitational field, if I went to the moon and threw it, it's going to take 6 times longer. What that does, you might give the same gradient, but we're stretching out our x squared efficient. Remember the coefficient of your x squared is like the dilation factor of your quadratic? Well, we don't normally go to the moon. Most of the scenarios in projectile motion, we have a locked x squared coefficient. It's always negative 9.8. However, if we went to Jupiter, it's going to be a squished quadratic because our acceleration is greater. If we go to the moon, it's going to be stretched out. Okay? In fact, there was a question in last year's WACE exam, a projectile motion question of a golf ball struck on the surface of the moon. And one of my brightest students who was up on stage at the beginning of this year, who got 99 point something ATAR, forgot that it was on the moon and used G equals 9.8 instead of 1.6. And he lost a couple of marks in the WACE exam. And he didn't realise until he got out and everyone's going, what about that question on the moon? And he went, ugh. He didn't even realise. It says, in 1971, a Apollo mission, blah, 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 struck a golf club off the surface of the moon. And he just read golf ball, height, time, solve. He didn't even realise that the context of the question was that the gravity value had changed. Anyway, on level ground, look at that. It comes to something so simple. Let's just go back to this. Does anyone recognise what this looks like? Yes. What does it look like from the... It's V. It's V. It's V. That is the velocity on impact. And remember we said it's plus or minus? Because the quadratic's saying that the discriminant here is negative square root u squared plus 2as or positive square root of u squared plus 2as. That's why it's positive or negative. Because there's 2 times that the gradient is there. You guys getting this? Is this fun?
Yeah.
Cool, because I freak out my year 11s with this and then I teach it in year 12. What do you recognise? What's that? The turning point. So all the quadratic equation, all it trickles down to in the context of projectile motion is how long it takes to get to its turning point and the speed of it at a given displacement. And what we do is we set it equal to 0. Yeah? We set s. That's, in maths, you go, what are we going to do? Oh, we've got to get everything equal to 0. Yeah? You got to throw you got something equals, throw it on the other side of the equal sign and make it equal to 0. In the context of projectile motion, we set s equal to 0. Set our displacement equation to 0, 0 equals, and it'll tell you the times that it's there. Yeah? Generally, we always solve for 0, but I could say, when was the object 2 meters high? Well, then what would you do? You would set it equal to 2. You would throw it across and it becomes a negative, and it would give you 2 times, and it might be, I don't know, there and there are 2 times when it was 2 meters high. Yes, Tristan?
When you say the turning point, is that the time or the displacement?
That is the time that the object was stationary. Okay? So, I'm showing you this, but it's not going to be in the test, so worry not. Just down the bottom here, oh look, I've given you all this space. Just down the bottom here, I'd like you to consider, I would like you to consider now if we were up a height and we threw something up and it fell down, like so. Okay? Now what we've done, if we include an initial positive displacement, this could be I'm out on the balcony of N block and I throw an object up and then it falls down past me and hits the ground. We would still get two times. You would get Tristan,
Yes, sir.
what would you like to be when you grow up? Have a think about it. And grow up. You get 2 times. 1 negative, 1 positive. Okay? Because now, if we add an s initial, the equation negative u plus or minus the square root of u squared minus 2a s. Now, this s value has changed. Now we're going to include the displacement of the object. Okay? Now, remember I said up here, what was it? Minus 4ac u squared. Really, I'm going to change that to minus 2as initial. Just, sorry to do that to you. I didn't know how much I was going to show you. Basically, I'd like you to set that as s initial, and then it still remains as a negative. Oh, hang on. No, it doesn't. Plus 2a s initial. Wait, let me think. No, it stays negative. We set that a term is always going to be minus 4.9. Just be careful with that. Wait.
G times
2g,
plus G times
2g s initial. Sorry. Okay. It gets, yeah, because a is a half of g and I didn't put the half in. Minus 2g s initial. Okay. We can still solve for it. The unfortunate thing is that now it doesn't simplify back to being, just a nice equation, because now s is a value and we have to consider it. And if s is positive, then we get a double negative here, negative 9.8, blah, blah, blah. So you get a larger time in the positive realm. I'd like you to have a go. Go back and work the first questions. I've left a bit of a space here because I'd like you to just very quickly sketch, okay, a position time graph. The first 2 questions are quite simple, but then the next questions below, I would like you to use the quadratic. Okay? So solve the first 2 questions using your Suvat equations, and then at the second part of this page, solve using the quadratic. Okay, so you've got a couple of questions to have a crack at. Please do so.